Dear students, I am Kavita BS, Assistant Professor, Department of Physics of Government First Grade College, Tiptur. In this session, I will explain the derivation of expression for coefficient of thermal conductivity. And this topic is in BSc course Physics subject, paper 3rd, Thermal Physics, Radiation and Optics 1. And this topic is in the lesson Thermal Physics of Unit 1. Let us start the discussion. That is the derivation of expression for coefficient of thermal conductivity. In the previous session, we have already discussed the derivation of expression for coefficient of viscosity. In the same way, we can derive the expression for coefficient of thermal conductivity. For that, let us consider a gas and it is at rest in a container of volume V and it is having the temperature gradient d theta by dy. Here the term d theta by dy represents the temperature gradient, that is nothing but the difference in temperature between the gas layers. And let us assume that the gas is made up of large number of closely spaced layers, and let us consider a layer at the layer at B, that is the gas layer at B, which is at a certain distance from the reference axis. OX represents the reference axis, and let the temperature of the gas molecules of the layer B is theta, and in steady state the temperature of the gas molecules along horizontal direction is constant, that is all the molecules of this layer will have the same temperature or at same temperature, and that is equal to theta. Next, here the temperature gradient is increases along vertical direction, that is in y axis. Then the temperature of the gas molecules is increases with in vertical direction. Then next, let us consider two more layers P and Q on either side of the layer B, and these two layers are at equidistance from the layer B, and that distance is equal to lambda, that is mean free path. We are considering the two layers P and Q on either side of the layer B at equidistance, and that distance is equal to mean free path of the gas molecule, and it is due to in order to avoid the collision while moving the gas molecules between the layers. Then the temperature of the gas molecules of the layer P is equal to theta plus lambda d theta by dy. Here the temperature of the molecules of the gas, that is the temperature of the gas molecules of the layer B is equal to theta, and the temperature of the gas molecules of the layer P is theta plus lambda d theta by dy. Similarly, the temperature of the gas molecules of the layer Q is equal to theta minus lambda d theta by dy. Then next, let us assume, or in the previous session we have already discussed about this part, that is in an average the number of molecules crossing in any one particular direction is equal to 1 by 6 of Nc. Here the term 1 by 6 mNc represents the total mass of gas molecules crossing the layer B either in upward or in downward direction per unit time. That is, a total number of gas molecules per unit volume is N, Then if it is total number, then in average the number of molecules crossing or moving in any one particular direction is equal to 1 by 6th of total number of molecules. Hence 1 by 6 Nc represents total number of molecules, and if you multiply the term by m, that is mass of each gas molecule, then it is equal to total mass of gas crossing the unit area of layer B either upward or downward direction in unit time, that is equal to 1 by 6 mnc. Here C represents average velocity of the gas molecules. Then next, the heat energy, then this represents mass. Then let us calculate the amount of heat which is either moving in a downward direction as well as in upward direction. That is the heat energy carried by the molecules of the layer P and crossing unit area of layer B in downward direction per unit time is equal to 1 by 6 mnc into theta plus lambda d theta by dy into Cv. That is the product of mass, temperature and specific heat capacity at constant volume gives the total heat energy carried by the molecules of the layer P and crossing unit area of layer B per unit time. Similarly, the heat energy carried by the molecules of the layer Q and crossing unit area of layer B in upward direction per unit time is equal to 1 by 6 mnc into theta minus lambda d theta by dy into Cv. That is amount of heat energy carried by the molecules of the layer Q crossing unit area of layer B in upward direction is equal to this much. Then next, the net amount of heat energy transferred in downward direction per unit area of layer B in unit time is equal to this term minus this one. Then on simplifying this, we get 1 by 6 mnc Cv, that is theta plus lambda d theta by dy minus of, this is common factor, that is 1 by 6 mnc is the common factor, then minus theta, this minus into minus become plus, that is lambda d theta by dy. Again by cancelling this theta with minus theta, then we get 1 by 6 mnc Cv into 2 lambda d theta by dy. Hence, on simplification, we get the net amount of heat energy transferred in downward direction per unit area of layer B in unit time, that is in this layer. Along this layer, the amount of heat energy transferred in the downward direction per unit area of layer B per unit time is equal to 1 by 3 rho C lambda Cv into d theta by dy. Here rho represents density of the gas, that is product of M and N. Actually this term is nothing but thermal conductivity. That means amount of heat transferred is nothing but thermal conductivity. Then by the definition, the quantity of heat flowing per unit time per unit temperature gradient is known as thermal conductivity of the gas, and it is given by, that is Q is equal to K into d theta by dy. That is thermal amount of heat is directly proportional to temperature gradient, and K is proportionality constant, and it is known as coefficient of thermal conductivity, and this is nothing but amount of heat flowing per unit area. Then in the previous equation we get that is equal to 1 by 3 rho c Cv into lambda d theta by dy. Then on equating these two we get, that is by cancelling this term on both sides, we get k is equal to 1 by 3 rho c Cv into lambda. So this is the final expression for coefficient of thermal conductivity. From this equation we can conclude that coefficient of thermal conductivity is directly proportional to square root of the absolute temperature. Since C here is average velocity. Average velocity is directly proportional to square root of t. In turn, K is also directly proportional to square root of t. And also, since C is inversely proportional to square root of the mass of the gas molecule, hence coefficient of viscosity is also inversely proportional to square root of mass of the gas molecule. So, this is about expression for coefficient of thermal conductivity. These are the textbooks for your reference. In the previous sessions also I have already mentioned these textbooks. Thank you.